Hi, in this video, we want to look at the concept of motion of connected bodies or how to solve problems involving pulleys. When we talk about connected bodies, we're simply referring to two or more bodies being connected by strings or rope passing over pulleys. We call them connected bodies because their motion are not independent of each other because they are linked. Understanding their motion will be the first step towards analyzing rail machines like the elevators, cranes, and conveyor systems. In order to study this type of systems, we use two complementary approaches, with the first one being the kinematic approach. Here, we use the geometry of motion. What we do basically is to find relationship between the acceleration of different bodies using the string length constraints. The second approach in analyzing this type of system is the dynamic approach or the kinetics approach. What we do here is to simply apply the Newton's second law to each of these bodies that has been connected together, where we introduce forces like tension, weight, and friction. Imagine we have two masses that are connected by a string passing over a pulley. What we're saying is if the first move, the second would move. Of course, not always in the same direction or with the same acceleration. But in this video, we're looking at how to break down the analysis on connected bodies step by step, from simple fixed pulleys to more complex moving pulleys. We'll start with kinematics, then we'll talk about the constraints, the constraints, and also how to analyze that to get acceleration, tension, weight, or the questions of static and kinetic friction. So we'll be starting with the Atwood machine, and we'll see how we can analyze systems like that. So given the Atwood machine on the screen, we're given two sets of masses, M1 and M2, connected together by light inextensible string, over a massless pulley. And then we're being asked to compute the value or the formula for the acceleration and also that of tension. Before we move on to talking about the acceleration and tension, let's talk about the light inextensible string and also the meaning of the massless pulley. For the light inextensible string, the first implication that we can take from this is that the string is actually massless, doesn't have any significant weight, or the weight is actually negligible. And for the inextensible part, it means the length is constant or true. The massless pulley also means this pulley adds no mass to the connection of M1 and M2. So simply M1 and M2 are simply connected or joined together by this rope or string. Now that we've talked about this, it's now time for us to compute the value of our acceleration and tension, or simply put, the formula to calculate the acceleration and tension. For the acceleration, we're going to pick a particular direction. So let's say the masses are moving or accelerating in this direction here. So that means I have an acceleration downward, and here I would definitely have an acceleration upward. Now we have to assume, since it is the same rope, the same acceleration we're having in A here will be the same in M1. So the acceleration we're having in M2 has to be the same acceleration we're having in M1. Of course, the direction is not the same, so they're only equal in magnitude. Now that we've picked a direction, then we can now apply our Newton's second law, the summation of the external forces being equal to the mass times acceleration. Now we're going to be looking at this system as a whole. So in this system as a whole, we're going to be trying to draw a free body diagram that would let us recognize all the external forces that are actually acting on these two masses. From statics, we know that all objects will definitely experience a weight force, or the force of gravity, which would always point downward. So for M2 will experience a force of gravity that we can call M2G, and definitely M1 also will experience a force of gravity that we can call M1 of G. Now that we've done this analysis, the next thing to look at would be to now apply the Newton's second law and see how we can generate an equation for our acceleration. Now, summation of all these forces, the only two forces acting externally in this outward machine, has to come from M2J and M1J. Of course, we have tension in the rope pointing upward, tension here also pointing upward. But since we're dealing with the external forces, tension is an internal force. So we simply come and say the M2J, the highest force, since we're moving in a clockwise direction. So M2J minus M1J would be equal to the summation of the masses M1 plus M2 in the bracket of A. Now, finally, deriving an expression for A would be equal to m2g minus m1g, everything divided by m1 plus m2. Now, this is the formula to calculate the acceleration in this machine, in as much as we've picked a clockwise direction. If we're picking a counterclockwise direction, then we just have to swap what we're having at the numerator. So instead of m2g minus m1g, it becomes m1g minus m2g all over m1 plus m2. So quickly, let's just write the formula for the acceleration on this side so that we can derive an expression for the tension in this machine, m1 plus m2. Now, clearing this place, it's time for us to get the tension. Now, getting the tension in this question, what do we do? Instead of taking the whole system now, we simply want to take a part of the machine. We can either take the part where we have this M2, at least I take my M2 when I have something like this, I have tension pointing up, and then I have my M2J pointing down. I can either take this part, or I can take the second part here, which comprises of M1. Whichever one you pick, you still arrive at the same answer. So let's take the right hand side of the system. So if you take the right hand side of the system, I suppose I have two forces now, two external forces, N2G and tension T. Since my object is accelerating, summation of all forces must be equal to MA. So I can say that the tension, or not tension, I can say M2G minus the tension must be equal to M2A. Now, since I'm trying to solve for tension, then I can take tension to the other side and bring M2A to this side. So that it looks like this, M2G minus M2A is equal to T. Now, since I have an expression for A already outside here, I can just solve everything or substitute the value of A here inside of this equation, and then I will be having M2G minus M2 in the bracket of M2G minus M1G, everything divided by M1 plus M2. Close the brackets, and this will be equal to the tension. Now, if you leave your answer like this, that's fine, but we can still simplify this expression to a more meaningful formula. What do we need to do? Since the operator here is negative, we need to find the LCM of these two fractions. So this, can simply say it is over 1. So the LCM of m1 plus m2 remains m1 plus m2. And then by time m1 plus m2, we divide it by 1, we still have this expression. We multiply it by the numerator, we'll be having m2g in the bracket of m1 plus m2. I close our brackets, and then m1 m2 divided by m1 m2, that's 1. So this is simply minus m2 in the bracket of m2g minus m1g. Now it's time for us to open the brackets. So opening this bracket would have, so I'm going to write my tension on the right hand side now. So here m2g times m1, we have m1 m2g, okay, and m2g times m2, so we have plus m2 squared g. So open this bracket, so we'll be having minus m2 squared g, and open these two brackets would have plus m1 m2 g. Now divide everything by m1 plus m2. Now you can see that this expression in the middle, you can cancel them out. M2 squared j positive, M2 squared j negative. So my tension T will be equal to m1 m2 g plus m1 m2 g over m1 plus m2. So finally, I can, since this is m1 m2, this is also m1 m2, I can then say my tension for this Atwood machine will simply be 2 m1 m2 g all over m1 plus m2. So you can see how simple it is in deriving our equation for both tension and the acceleration given an Atwood machine. We'll be moving on to the second system. So let's say we're having a box placed on a smooth horizontal surface connected with a pulley to another box, M2. So we have masses M1 and M2 connected over this pulley using an inextensible light string. M1 has been placed over a smooth horizontal surface, while M2 is free to lying freely, or M2 is suspended freely through the string. Now, just like we did in the previous example, the first thing is to choose direction. So let's assume that my system will accelerate towards this way. Okay, if my system will accelerate towards this way, then I want to compute the forces I'm having in this system. For M2, the external force acting on M2 would come from its weight, or the force of gravity on itself. So here we have the M2J, and then we have an internal force in terms of tension, since we're connecting this M2 over this pulley using a light inextensible string. Definitely, I have tension also in this direction, but the tension in M2 would also be the same tension in M1 because it is the same rope. For M1, I have the force of gravity pointing down, F of G, or I can simply write it as M1G, and I have an upward force, the force at the horizontal table exerts on M1, so I'll call that R. All right, so now that I've written the forces I'm having in my system or connected system, it's now time to apply Newton's second law of motion, the summation of all forces or all external forces being equal to the mass times its acceleration. So first thing I want to do is to look at the external forces. Here I have M2J, internal force tension, internal force tension. Now these two forces, M1J and R, are also external forces, but they are balanced. Balanced in the sense that M1 is not moving up or moving down. It is basically resting vertically on this table. Now, M1J and R are not responsible to make this object or to make this box accelerate in this direction. So we're going to be neglecting it as it is not useful in this analysis. So it means that the total force or the only external force I'm saying in this system must come from M2J. So there I can say M2J would be equal to the set of masses, that is M2 plus M1 in the bracket of A. What this means is the force or the only force responsible to make these two systems, or to make the system rather, move in this direction is M2J. So computing our acceleration, A now will be equal to M2J divided by M1 plus M2. Now that we've gotten the acceleration, it's now time to get the tension. To get the tension, we're going to be excluding the system, or we're going to be taking just one part of the system. We can either take the one applying to the M2 box or the one applying to the M1 box. So since we took M2 in the last example, then let's take M1 in this example. So we can see that the only force acting on M1 is the tension force, and my M1 is accelerating towards the right. So I can say T must be equal to M1A. Now, since I have an expression for the acceleration here, why not just write it inside of this equation and derive the formula for the tension? So here we have M1 in the brackets of M2G divided by M1 plus M2. Now, after multiplying this, the tension we'll be having here will simply be M1 M2G divided by M1 plus M2. So this is the formula to calculate the tension in as much as my object or my system is connected in this method or manner. In the third example, we'll be looking at what if this table is now rough. This time around, we pick smooth. In the next example, we want to look at it when the table is rough. For our third example, we're told that block of mass M1 and M2 are connected by a light inextensible string over a massless pulley, and block M1 is placed on a rough surface. Now, if this block is placed on a rough surface, it must mean we have one more external force acting in this system. Originally, we've seen how we arrived at the M2J, which is the force of gravity on M2. We've seen how we arrived at the tension. We've seen how we arrived at the tension applying to M1. We've seen how we arrived also at M1J. We've also seen how we arrived at R. Now, the last external force acting on this object or this system has to be the kinetic friction. So, and it always opposes motion. If my box is accelerating this way, then the frictional force, let's call it Fk, will accelerate in the opposite direction. Now we can now compute our acceleration. Now, before we do that, we must note that the force of friction or force of kinetic friction will be equal to the coefficient of kinetic friction, mu k, times the normal reaction. So instead of writing Fk, we can write it as mu k of R. All right, now let's take the summation of all external forces being equal to mk. So here, since my object is accelerating this way, so I'll have m2g minus mu k of R. This must be equal to m1 plus m2 in the bracket of A. Making A the subject of the formula, we have A equal to m2g minus mu k R all over m1 plus m2. So here we've gotten an expression for the acceleration in this particular system. It's time to compute our tension. For us to compute our tension, we can take any mass here and exclude it from the system. That is, we can either use M2 and look at the forces acting on M2, or we use M1 and look at the forces acting on M1. Since we used M1 in the previous example, let's use M2 in this example. Note, whichever mass you decide to use, in as much as you compute the forces acting on the mass correctly, you arrive at the same expression for the tension. So taking the mass M2, we have M2G minus T, and we say this will be equal to M2 of A because my object is accelerating. Now, after writing this, I can take the tension to the other side and bring M2A to the left-hand side. So we have M2G minus M2A, and this will be equal to the tension. Since we have an expression for the acceleration already, we can substitute that into this formula by having M2 dot M2G minus mu K of R over M1 plus M2 and close the bracket. Now, simplifying this, we would have the tension will be equal to the LCM of these two would be M1 plus M2, and this multiplied by this would have M2G in the bracket of M1 plus M2. Simplifying the expression, this expression will be having minus M2, open bracket, M2G minus mu K of R. Now, if you leave your answer like this, or if you leave your expression like this, it is right. But we can still simplify to something much more refined. What do we mean? M2G times M1 will have M1 M2G. M2G times M2 would have M2 squared of G minus M2 times M2 will have minus M2 squared of G, and minus M2 by mu KR would have plus M2 mu K R, and everything here divided by M1 plus M2. Finally, we can see that we can cancel out this. We can also cancel out this. Also, we can factorize. We have M2 here. We have M2 at this particular point. So my tension can be equal to M2, open brackets, M1G plus mu K R, everything divided by M1 plus M2. So this is the expression for the tension in this system. And this is the only equation we can generate? Definitely not. Since we are dealing with friction, we have the ability to generate two more formulas. We've talked about one here, Fk is equal to mu k of R. The second one is to find R. So R will simply be equal to, R is equal to M1 of G. So this is another equation we can generate from this system, depending on what we are asked for. The question is asking for the normal reaction. This is the equation we want to use. The question is asking for the coefficient of kinetic friction. Then this is the equation we want to use. The question is asking for the acceleration. Then we want to use this equation. And if the question is asking for the tension, then we want to use this equation. In the next example, we're looking at how we resolve questions when we have a block of masses placed on an inclined plane. For this, we have two masses connected by a light inextensible string over a pulley. It's block M1 resting on an inclined plane and M2 being suspended freely by the rope. We're going to be doing the same thing we've done in previous examples. We're going to be trying to compute the expression for the acceleration in this system and also for the tension in this system. Note, we have to take the surface of this inclined plane to be smooth, a smooth inclined surface. Now, if it is smooth, we already know from geometry that the first force I have acting on M1 has to be the normal reaction R1. Now, if I have R acting on M, it must mean that I have the force of gravity acting downward in terms of M1 of G. Now, this doesn't look like downward when you look at it. So if we're talking about downward, then downward must mean that this is this. Now, what does this mean? It simply means we have to resolve our forces. Now, we already know from geometry that if this angle here is theta, then definitely the angle between these two lines have been drawn would also be theta. What's that to tell us? It means this one pointing down will simply be mg cos theta, and the force acting on this box, making it wanting to slide down the inclined plane, would be mg sine theta. If you are wondering why the force responsible for making this box slide down to be mg sine theta and the one pointing down being mg cos theta, it's because the angle we are given here is to the vertical. If we decide to draw a line of axis x and y along R and M1 of J, we'll notice that the theta we're given is to the vertical, not to the horizontal. Hence why we are switching the mg cos theta and mg sine theta. Of course, this should be m1j cos sine theta and this should be m1j cos theta. Now for this block of mass M2, what are the forces, external forces acting on it. So it still has to be the force of gravity or its weight force. And this will come in form of m2g. Now that we've written the external forces acting here, it's time to pick a direction for our acceleration. If my object is accelerating downward in this way, so definitely this must mean that to compute our acceleration, we'll be using the m2g minus m1g sine theta, and this will be equal to m1 plus m2 in the bracket of a. We already know why it will be the same acceleration in both cases, because it is connected by the same rope. If they're connected by different ropes, then definitely they'll have different tensions and then they'll have different accelerations. Now that we've computed this, it's time for us to get our acceleration. So getting the acceleration, we'll simply divide both sides by m1, m2, and then we'll have m2g minus m1g sine theta all over m1 plus m2. So this is the expression for our acceleration. Note, this is because the plane is smooth. The inclined plane is smooth. If the inclined plane were to be rough, then after showing all my external forces here, then I have to include another external force in form of the force of kinetic friction moving in the opposite direction of motion. So it must mean that at that stage, we'll be having m2g minus open bracket m1g sine theta plus the force of kinetic friction. But since we're told that this inclined plane is smooth, so that's why we're having our acceleration as m2g minus m1g sine theta divided by m1 plus m2. Now, to get our tension or tension in this rope, what do? We simply take a system. So this time around, we'll be taking this system M2. And taking this system, we're going to be analyzing it separately. So what do we mean? We know that we have tension moving up, also have tension moving in this direction. Since I have acceleration in this case, it must mean that m2g minus the tension force will be equal to m2a. Now I can bring m2a to the other side. It becomes m2g minus m2a is equal to the tension force. Since we've derived an expression for the acceleration in this system, then we can say m2g minus m2 in the bracket of m2g minus m1g sine theta, everything divided by m1 plus m2. Now, simplifying this expression, would have the tension equal to the LCM of both denominators would be m1, m2, and this becomes m2g in the bracket of m1 plus m2 minus m2 in the bracket of m2g minus m1g sine theta, close the bracket. Now it's time for us to simplify further. Of course, as always, if you leave your expression like this, you still arrive at the same answer. But why not make your expression much more readable? Expanding these brackets, we'll be having m1 m2g plus m2 squared g minus m2 squared g and plus m1 m2 g sine theta, everything divided by m1 plus m2. Now, the expression for attention, you can say this cancels out. Here I have m1 m2g, here I have m1 m2g. So it must mean I can factorize that outside in such a way that I have m1 m2g. If we take this divided by this, we'll be left with 1 plus, and then I'm left with sine theta, everything divided by m1 plus m2. So we've successfully computed the expression for the tension in this system. Now, for our fifth example, we're going to be looking at the connection of a fixed pulley with that of a movable pulley. So when we have a fixed pulley and that of a movable pulley. So for this example, we're given a two-pulley system. Now you notice that the first pulley, let's call this P1, is fixed at this end, while the second pulley is movable. Because in the question, we're told that both pulleys are massless. Now, the same thing we did in the previous examples. We want to get the acceleration of the system or generate an expression for it, and also generate an expression for the tension in the system. But you have to be careful. Here we have different acceleration. The acceleration at this pulley system will be different from the acceleration in this second pulley system, because it is not the same tension, it is not the same rope. So since they have different tensions, then definitely you'll have different accelerations. Now we're going to be applying the string constraint in solving this. It's quite easy if you've done calculus. If you've not, still quite easily. if you can follow the approach carefully. Now, for the string constraint approach, we're going to be taking each individual pulleys now. We're taking each individual pulleys. Remember, when we started the whole discussion, we said since it is connected, or the masses are connected together by a light inextensible string, then it must mean that the length of the string doesn't extend no matter how you stretch it. What do we mean by that? So let's say we're to just draw a line of symmetry where this pulley is formed, and then we decide to get the length of this string at this particular junction. Let's say we call it x1, and we decide to get the length of this string also, and let's say we call this x2. We're saying when we add x1 plus x2 together, it gives us the total length of the string. Let's call this L1. Now, no matter where this string is, no matter where this mass is, if x1 is increasing, it must mean that x2 is decreasing in the same proportion because the length of this string is constant. Now that we know this, what happens when we differentiate displacement twice? If we are to differentiate this expression, we'll come to find out that the squared x1 over the t squared plus the squared x2 over the t squared equal to the squared L1 over the t squared. Now we have to pick a direction. We can pick upward direction to be positive since we know that there will be an acceleration in this pulley system. Now, if you assume that we have an upward acceleration, that is, we're picking upward to be positive, then definitely it must mean if we're coming down, or if our object or mass is coming down, it will have a negative acceleration. That said, since we have an acceleration in this string and we also have an acceleration in this string, now the acceleration in this string will also be the acceleration of this pulley. So I can call the acceleration here A2. Now let's see the relationship between A1 and A2. Like we said, if we differentiate twice with respect to time, displacement, we are going to be having acceleration A1, which will be positive. Now, what happens when we differentiate a constant? Remember, we said the addition of the length x1 plus x2 would always be equal to a constant. So if we differentiate a constant, would always return 0 value. Then we're left with d squared x2 over the t squared. Now this must mean that d squared x2 over the t squared will be equal to negative a1. What does this mean? It means if this mass m1 is accelerating downward, then this pulley or the acceleration in this string, if this mass m1 rather is accelerating upward, then the acceleration in this pulley or in this side of the string must be downward. Since it is the same string, then definitely we can say A1 would be equal to negative A2. That's the first conclusion we can make from here. How do we get this? We've been talking about this. We've been assuming this since the first example. Since they are the same string, then if the object is accelerating downward, then this one is accelerating in the opposite direction. So this is just a way to prove what we've been saying so far. So I'm going to write that at the top here, A1 equal to negative A2, and clear the screen so we can analyze what is going on in the other part of the pulley. So now that we're done with this, part, this mass M1, now for mass M3 and M2, since this is a different pulley and definitely different length, then we want to apply the same string constraint to getting the acceleration in this part. So let's assume that we have an acceleration in this mass pointing coming downward. So if the acceleration here is coming downward, just like so let's reverse that. So the acceleration here is coming upward, so mass M3 coming upward, so as an acceleration of A3. Now we want to compute what is actually happening here. So again, we're going to be getting the length of this string. Okay, so let's call the length here x4 and the length of mass M2. So we can call that x. Okay, let's call this x4. Let's call this x3. So for sake of simplicity, okay, so let's try and do this. Okay, so this is x3 and this is x4. Now remember, when they said upward, when we have acceleration moving upward, then we take it as positive, and we have acceleration moving downward, we take it as negative. Now, if I were to find the length of this mass M2, the string, in this pulley, holding M2 to the second pulley, then I can come and say x4 will simply be x4, or you can say the length of this string from this point to this point. Since the length here is x2, I can say the remaining length in this expression will simply be x4 minus x2. If this is x2, from this point to where my pulley is starting from, we've called it x2 already. And from this point to where mass M2 is starting from is x4. So it must mean this remaining part will simply be x4 minus x2. Okay, we add it to, again, do the same thing for the length here. So here we'll simply have x3 minus x2, and then this will be equal to our second length. Remember, we did the length of x1 plus that of x2. We said it should be equal to L1. Now, since this is also a light inextensible string, then definitely by the time we have the length here plus length here, it must be equal to a constant. Now, what do we know here? We can say x4 plus x3, by the time you open the bracket, minus 2x2 will be equal to L2. Now, before we move further, differentiating this expression, let's find out what we think from logic, what our acceleration in A3 would be. Now, since A2 is coming downward and A3 is moving upward, so we can say, or we can come to another conclusion, that our acceleration in 3, or the M3 acceleration, would be equal to the negative of the A2 acceleration. So when we have A3, the same thing as writing it and saying negative A2. Now, this said, let's now differentiate this expression. If you differentiate twice, that is d squared x4 over the t squared plus d squared x3 over the t squared minus 2d squared x2 over the t squared equal to d squared L2 over the t squared. Now, what do we know? When we differentiate x4 twice, definitely we're having the acceleration in 4, which you don't know, but that's what we want to find. Now, if you differentiate this also, we'll be having x3. Differentiate this also, we'll be having negative 2 x2, or sorry, negative 2. So this should be a3, not x3. a3, negative 2, a2, and then this is equal to. So we know that when we differentiate a constant, we always have 0 value. All right, so time for us to put in a missing unknown. We already said that a2 is the same thing as, what's it called? A2 here would be the same thing as negative A1. So A2, same thing as negative A1. So here we can write this A2 and write it as negative A1. So here we have A4 plus A3 minus 2 in the bracket of negative A1 equal to 0. Yes, simplifying this, we have A4 plus A3 would be equal to, so negative, that becomes positive, and when it goes to the other side, it becomes negative back, so negative 2A1. Now, since we have an expression for A3 to be negative A2, then we can simply come and say the acceleration for A4 will simply be equal to negative 2A1. Okay, so if A3 goes to the other side, it becomes negative A3. By the time you negate A3 again, it becomes plus A2. So this is the acceleration in this particular part, minus 2A1 plus A2. So we've gotten the acceleration in the whole system. It's now time for us to generate our total acceleration, or the formulas to calculate the acceleration in this system and also the tension in this system. Now, to do this, what we simply want to do is to look at the block of system individually. So for the mass M1, since we have tension moving up, let me call this tension T1. The tension here is coming in this direction. Let's call it tension, okay, also T1, because it is the same rope. Now this tension T1 applies to both the left hand side and the right hand side. For the second pulley, I have tension T2 moving in this direction and tension T2 also in this direction. So time for us to generate our equation. For the first equation in this system, we'll be having T1 minus mg, or m1j, would be equal to A1. So this is our first equation. Okay, T1 minus M1J is equal to A1. For the second equation, we can derive from this. If you block this system, and just take note of the external force. Remember, this pulley is massless, yes? But then, since we have two forces acting on it, the tension and 2 times the tension in this scenario, but since the pulley is massless, we can say our second equation will be gotten by T1 minus 2T2, and this would be equal to 0. T1 minus 2T2, and this will be equal to 0. So this is our equation 2. Now for equation 3, here I have T2 acting on the block of mass M3. Now since we're moving up, so we can say T2 minus M3, T2 minus M3G, this will be equal to M3 in the bracket of A, or negative A2. So okay, we don't have to write the bracket. So since we already said A3 is equal to negative A2, so we can just say negative M3A2, and then this will be our equation 3 in this system. And lastly, the last equation will be having again upward positive, downward negative. So we have T2 minus M2G, and this will be equal to M2 in the bracket of the acceleration. So the acceleration here is given as minus 2A1 plus A2, and then this is our equation 4. So with these 4 equations, you can see we have 4 unknowns. We don't know what T1 is, we don't know what M1 is, we don't know what A1 is, we don't know what T2 is, we don't know what M3 is, we don't know what A2 is. But typically in the question, we're given the masses M1, M2, and M3. The only unknown we'll be having here will be T1, A1, and T2, A2. So since we have 4 unknowns, then definitely with these 4 equations, we can solve the set of unknowns. So this is how we analyze questions or problems involving pulleys, especially when you have a fixed pulley and a movable pulley. So if this video has been helpful to you, and then you feel you've actually gained something, you can do well to like the video. If this video has not been helpful to you, just don't do anything. Thank you for watching, and bye bye.